Continuing on with the atmospheric makeup here, we get to something called the ionosphere. And this is in regions of the thermosphere, molecules are heated by ultraviolet radiation and other radiation from cosmic rays. These are extremely powerful radiation, comes from deep space. If you are a Marvel fan, you may have heard of cosmic rays in relationship to the Fantastic Four. Cosmic rays do not cause superpowers, just to point that out. But makes for a good story. And these cosmic rays, there are different types of radiation. They also break apart the molecules, stripping electrons, and other thing, causing the air to take on the form of something called plasma, as you see in number 2. This is a special state of matter made up of a mixture of electrons and positive ions. Another name for positive ions there is cations. And so we kind of have some unique things because of this ionic state of molecules. This portion of the atmosphere is called the ionosphere. Much of its substance is composed of ions, and the ionosphere can act like a giant mirror, bouncing certain types of radio waves back down towards the ground. Now, I hope it's apparent that it's not all radio waves, because we have radio waves that go up into bouncing off satellites and such, but the ionosphere can do it as well. If radio waves of a certain length hit it at the right angle, they can be bounced back. I had a friend in high school. He was a ham radio operator. He said normally his ham radio went a long ways, but there was one day he actually reached somebody in Japan, and that was from Oregon. So the radio waves got bounced pretty well. This is also why some radio communications can be disturbed when stuff happens with the sun, solar flares and the like. It can cause fluctuations and activity in the ionosphere, resulting in disturbances with radio communication. Another thing, so that's a special feature about the atmosphere. Another special feature is something called the magnetosphere. It's the fact of the matter is that our planet is a magnet. And magnets have magnetism concentrated at 2 points known as poles. Now on the Earth, that would be concentrated at the magnetic north and south pole, which is not the same as the geographic north and south pole. I know magnetic north pole is somewhere over, I think it's Baffin Bay in Canada, northeastern Canada. It does not, that's where the center is. That's where or not center, but that's where one of the poles is and where the magnetism emanates from. Any magnetic item has a magnetic field that surrounds every magnet. It is a region in which the magnet affects other objects. So when you put iron filings in this region around a magnet, they line up in certain ways based on the lines of the magnet, what shape the magnet is. The magnetosphere is the Earth's magnetic field, and it is influenced by solar winds. Now these are not winds in the same term as air particles flowing off, but they are particles flowing away from the sun. Many cases it is ions and such like that are being blasted off the sun as stuff explodes on the sun and moves away from it. The solar winds actually cause our magnetosphere to be oddly shaped. It is not a perfect sphere. In the picture here, you can see some of that solar wind coming off, and it compresses the magnetosphere that is between the Earth and the sun, forming almost an egg shape when you consider the entire magnetosphere instead of a round shape. The magnetopause, see that pattern again? Magnetosphere, magnetopause, is the upper boundary of the magnetosphere, pretty much where that kind of greenish purple hue is on the very outward part of that. Now, the magnetosphere does some interesting things. Because it is magnetized, it is a magnetic field, it will attract ions because they are electrically charged, and there's a correlation there. And one of the effects that we see of that is the auroras. Auroras are particles from the solar wind that react with particles from the Earth's atmosphere, creating these dancing lights that are actually very beautiful and many different colors. The aurora borealis is northern lights. The aurora, and that should be australis, not Australia, should be the aurora australis, is the southern lights. Boreal, I believe both boreal and Australia are Greek words, boreal meaning north, austral meaning south. So we can't have lights at either end there. And really, what kind of happens is the ions get funneled into to the magnetic poles, reacting with stuff, becoming more highly ionized and all that kind of thing. And then light comes off as a result. Another interesting tidbit about the magnetosphere is we get these Van Allen radiation belts. They're named after James Van Allen, who discovered the inner belt in 1958. And sometimes what happens is that solar wind particles get trapped in our magnetosphere, and they just kind of they orbit the Earth. These magnetic belts are harmful to people and instruments. So we do not send people up there to explore them so much, but we have learned about them to a great extent. The inner radiation belt begins around 4,000 miles above the Earth's surface and is the smaller region marked by the red on the diagram here. The outer radiation belt is much larger, marked by the blue area there. The lines are just magnetic field lines trying to depict what the way they come off and come back into the Earth there. The International Space Station and other satellites orbit beneath the inner radiation belt, so between the Earth and that first radiation belt. Some satellites orbit between the two belts. They manage to get them past the first one, orbiting between them. If spacecraft must be sent through the radiation belt, the amount of damage remains small as long as the spacecraft travels through those belts quickly, which really, if we're sending spacecraft through the belts, we really want them to go by quickly anyway. So as the distances in space are very large, we don't want to spend a lot of time waiting around. Atmospheric pressure. One other factor about the Earth's pressure, or Earth's atmosphere, is that there is pressure. It's the amount of pressure resulting from the weight of air above an object. At sea level, it's around 14.7 pounds per square inch. Roughly the size of your thumbnail. That's a square inch, give or take. I mean, depending on how big your thumbnail is. Let's see. This is equivalent to an almost 15-pound bowling ball resting on every square inch of your body. But even though tons of air press against your body in all directions, you are not flattened by the weight. Our bodies are designed to take advantage of that weight. Certain features are a result of that pressure keeping everything in its place, which is one of the problems when we go to space and there is no pressure. That's why they have to wear those protective suits to keep pressure on their body. As altitude increases, pressure decreases. The air surrounding the Earth is thickest at the bottom of the atmosphere, thinnest at the top. The weight squeezes a certain amount of air into a much smaller volume at lower altitudes than it does at higher altitudes. Although the atmosphere extends upward for hundreds of miles, half of the air is located below 3 miles. And all but 1% of the air is below 20 miles. Thus, the upper layers of the atmosphere have very few air molecules. Even before reaching the mountaintop, you would sense that pressure was decreasing if you were climbing a mountain. Whenever you've gone into an airplane or maybe you've driven over mountains before and your ears pop, that's a sign of a difference in pressure. Some air kind of gets trapped inside your head between your ear and your mouth. And when you get up to a certain altitude, the air pressure is so little that when it changes, it does it very quickly, and it causes that popping noise. If the air pressure doesn't equalize like that, it can be very problematic. My wife and I went on an airplane ride. She was not feeling well at the time. We were visiting family around Christmas time, and her ears would not pop. She was miserable throughout the entire flight, and it was several hours after we landed that her ears finally started normalizing and the pressure in her head decreased. And she was actually feeling a little bit better as a result. At high altitudes, many recipes for baked goods often require adjustments because of the lower air pressure. If you've ever lived in places like Denver or high up in altitude on any mountain, then you have possibly seen on directions for cooking that there might be like mountain directions or high altitude directions. And usually it requires cooking at a higher temperature for a longer period of time because water boils, especially if you're boiling water, while water boils at a lower temperature at those higher altitudes. So that is it for this last little section of 7.1. Don't forget to answer the science video question so that I know that you have watched this video and have possibly, if you're smart, taken notes.